Good morning, everyone. We are Kurt McLeod, Tyler Portfield, and Michael Underwood, and myself, Eduardo Chapa. And today we are excited to present an emerging frontier in construction technology called Shotcrete 3D printing, or often termed robotic shotcreting. In advanced concrete placement, few technologies offer the blend of geometric freedom and structural performance as does shotcreting. Our presentation will bridge the gap between traditional shotcrete methods and advanced robotic applications currently being developed. Let's quickly look at our agenda. Our discussion is structured into two main phases. First, we will conduct a brief review of traditional shotcreting, what it is, how it works, and why it is used. This foundational knowledge is crucial. We will also formally define shotcreting, 3D printing. Second, we will move into a deep dive. We'll analyze the demanding material considerations specific to robotic applications, conduct a direct comparison between Shotcrete 3D printing and the more common concrete extrusion methods, and finally, look at the most exciting modern applications and the future outlook of this technology. Let's start with the basics of traditional shotcreting. Shotcrete is not a material, it's a method. Invented back in 1907, the process fundamentally involves pneumatically projecting concrete or mortar onto a surface at a very high velocity. The key difference from conventional concrete is the high kinetic energy of placement. Unlike concrete that is poured or pumped and then vibrated, shotcrete is placed and compacted simultaneously, all in one action. This method has three critical characteristics that define its utility. First, the high velocity application. This is what makes it unique from traditional concrete pouring. The second, simultaneously placement and compaction. The high impact force densifies the material, leading to high compressive strength and low permeability. Lastly, there is no formwork required. The material is designed to be self-supporting, making it ideal for curved overhead or complex structural elements like tunnel linings and dome roofs. To achieve this, the mix design and application process must be carefully controlled, which leads us to the two main processes, dry and wet mix. Traditional shotcreting is broadly classified into two distinct methods, dry mix and wet mix. Understanding these differences is key to appreciating the transition to robotic systems. In the dry mix process, all ingredients, cement, aggregates, and admixtures are thoroughly mixed before being introduced into the delivery hose. Water is the last ingredient added by the nozzle operator right at the point of discharge. The advantage here is control. Since the operator controls the water ratio, they can quickly start and stop the process, making it best suited for small repairs or situations where intermediate applications is needed. However, it results in higher rebound, which is the material that ricochets off the surface, essentially waste. Conversely, the wet mix process premixes all ingredients, including the water, before pumping the slurry down the hose. Compressed air is introduced only at the nozzle to increase the velocity. The wet mix process offers better consistency, less dust, and is ideal for high volume applications like long tunnel linings. Crucially, the wet mix is the system that has been the most successfully adapted for large-scale automated robot shotcreting due to its highly controlled continuous pumping mechanisms. Let's explore where these traditional methods have been indispensable. For over a century, traditional shotcrete has been the go-to solution for challenging construction environments. Its primary domain is tunnels and mining. When you excavate rock, shotcrete is often the fastest, safest, and most effective way to provide immediate primary structural support to prevent cave-ins, thanks to its rapid application and strength gain. Secondly, it is the industry standard for constructing pools and tanks. If you have ever swam in a concrete pool, it was almost certainly built using shotcrete. The method allows contractors to easily form complex curved geometries for swimming pools or water-retaining tanks without expensive and complex formwork. Finally, it is essential in repairs and stabilization, whether it's strengthening aging bridge, stabilizing slopes with retaining walls, or reinforcing existing concrete structures. Shotcrete offers excellent bonding materials and strength density, essentially becoming an integral part of the original structure. To summarize the benefits, shotcrete offers three key advantages. The first, high strength and low permeability. The pneumatic application compacts the material, resulting in superior mechanical properties compared to many cast-in-place concretes. The second is its excellent bonding. It adheres aggressively to almost any existing substrate, making it a perfect solution for repairs and overlays. The third, it conforms to irregular shape. This is its geometric superpower. It can build curves, domes, and free-form shapes where traditional formwork would be prohibitive, complex, or costly. However, it's not without its challenges. The first is its high equipment costs. The machinery required, powerful pumps, compressors, and specialized mixers are expensive. Secondly, it requires expert skills. The quality of the finish and the material compaction is highly dependent on the skill and consistency of the nozzle man. It's an art form. Lastly, material waste or rebound. As noted, material inevitably bounces off the surface, which increases waste and costs, especially in the dry mix process. These challenges, particularly in the need for human skill and the inconsistency it can introduce, are exactly why the industry is now turning to robotics. This brings us to our next section, the true definition of shotcrete 3D printing.
What is shotcrete 3D printing? Shotcrete 3D printing consists of 5 main phases. 1. Model creation. The second phase will be the material preparation of the mix design. The third will be the pumping of the material and then the nozzle delivery. 4 will be the distribution of the material layer by layer. And finally, the last phase will be quality control and modifications as needed. Model creation. Shotcrete 3D printing starts long before any material ever touches the job site. The process begins in a fully digital environment where a CAD or BIM model is built to capture all the details, such as geometry, dimensions, openings, and reinforcement layers. Once the model is complete, it's sliced into horizontal layers, similar to traditional additive manufacturing or 3D printing workflows. The slicing software determines things like layer height, bead width, deposition rate, and nozzle path. These parameters are crucial because they directly affect print quality and the structure behavior of the finished element. During this stage, the software also checks for potential collisions and errors that could become present during production. Material preparation. Material preparation is one of the most critical parts of the Shotcrete 3D printing process. Shotcrete 3D printing typically uses a wet mix shotcrete that must pump smoothly through hoses while gaining strength quickly enough to support rapid layering. The most commonly used materials include cement, fine aggregates, water reducers, plasticizers, and sometimes supplementary cementitious materials. Fibers can be added for toughness or tensile capacity, but the key ingredient is the set accelerator. This allows the material to stiffen almost immediately after impact without compromising pumpability. Proper mixing ensures a uniform and stable material. Too much water reduces buildability and weakens interlayer bonding, while too little can cause clogs or poor flow. Continuous mixing may be used to maintain consistency during the printing process. Pumping and nozzle delivery. Once the material is mixed, it moves into the pumping and nozzle delivery phase. High-pressure pumps push the wet mix through long lines, sometimes across significant distances or heights. This gives shotcrete printing a major advantage over your typical extrusion-based 3D printing. When the material reaches the nozzle, an accelerator is injected into the spray stream. This allows the mix to stay pumpable up to the very last moment and then stiffen immediately when applied. The nozzle uses airflow to shape and compact the spray pattern, improving density and interlayer adhesion. Standoff distance, spray angle, and travel speed are precisely controlled by the robotic arm to maintain consistent dimensions and geometry. Because the shotcrete is projected at high velocity, it self-compacts on impact, eliminating the need for any vibratory tools. This stage directly influences density, bond strength, surface quality, and the finished structural performance. Layer by layer distribution. With the material delivered and compacted, the structure is built one layer at a time. As the nozzle follows its programmed path, thin layers start to build up and form the full geometry. Each layer must stiffen quickly enough to support the next. Shotcrete's fast-setting behavior allows printing without or with minimal formwork. This enables more complex, free-form, or curved geometries compared to conventional construction. The robotic system tightly controls layer spacing, bead width, and deposition sequencing. In some cases, specific patterns such as zigzags are used to enhance the structural performance or manage different stresses. Because the process is robotic, dimensional accuracy and repeatability remain high throughout the entire print. This layer-based approach is what gives Shotcrete 3D printing its flexibility, speed, and ability to handle complex designs. Quality control and modifications. Throughout printing, quality control happens continuously and in real time. Modern Shotcrete 3D printing systems rely on sensors, cameras, and laser scanners to monitor each layer. These tools can measure bead height, width, texture, and the nozzle's distance from the printed surface. If the system detects issues like excessive slump, uneven layers, or drift in the nozzle position, the robot automatically adjusts speed, standoff distance, or movement path. The pump can also modify the material output rate. Environmental factors such as temperature, humidity, and wind are monitored as well, since they do influence curing and spray characteristics. After printing wraps up, additional checks are performed. Rebound measurements, density, and evaluations of interlayer bonding. These quality control procedures ensure the printed elements meet structural and performance requirements before moving into any post-processing or construction integration.
Now that we've covered the process, let's dive into one of the most critical aspects of Shotcrete 3D printing, the material considerations. The success of this technique hinges on the balance of two opposing material properties, workability and buildability. First, workability refers to how easily the material can be pumped and sprayed for the material to flow smoothly through the high-pressure lines and nozzle. We require low viscosity for pumpability. To achieve this smooth flow, we often rely on chemical admixtures, most notably superplasticizers to ensure the correct flow rate. Another key factor is the aggregate. We prefer fine aggregates to significantly reduce the risk of nozzle blockage during the printing process. However, the material also needs buildability, which is the ability to support its own weight immediately after placement. This is essential for printing vertically overhanging structures. To achieve this, we introduce accelerators into the mix, which are critical for increasing the material settling time, meaning it sets and gains strengths much faster. This rapid settling must provide a high yield strength to withstand the vertical load pressure from subsequently layers being deposited on top of it. It's a delicate balance, making material design a complex engineering challenge. Beyond workability and buildability, two other crucial material factors are bonding and durability. Unfortunately, the interlayer bonding is often considered the weakest link in Shotcrete 3D printing. The printing layer must bond securely to one another to create a strong structure. To maximize this bond, we must minimize the time delay between placing interlayers. If too much time passes, the previous layer begins to set, and we also have to see the negative effects of water dehydration, which can weaken the bond. For overall durability, we need to optimize the water to cement ratio. A correct water to cement ratio helps to reduce capillary voids within the concrete, which are a major contributor to cracking and decreased strength. Finally, we begin to use chemical admixtures, specifically accelerators, to ensure the final product is durable, as they play a key role in rapidly building the required early and final strength of the printed structure. To address these challenges, researchers are investigating a range of materials for Shotcrete 3D printing. The most common and preferred material remains cementous or Portland cement. However, we are also seeing interest in more sustainable options like geopolymers and magnesium oxide cement. Geopolymers require thermal curing, but magnesium oxide cement offers the attractive features of rapid strength development. Moving toward advanced composites, we have engineering cementous composite, ECC, which is a fiber reinforced to enhance its properties, but its main drawback is its high cost. On the high performance end, there is ultra high performance concrete. UHPC is desirable for exceptional high compressive strength and flexural strength, which opens up possibilities for structural and load-bearing elements in 3D printing. Each of these materials presents a unique set of benefits and challenges that we must consider depending on specific applications.
Everyone, my topic today is applications of Shotcrete 3D printing, either proposed by past researchers or new ideas developed by the group members. So let us go into the introduction of applications of Shotcrete 3D printing. And there are two distinct ideas of Shotcrete 3D printing, and it's found in residential and commercial applications. Some examples are office and residential buildings, structures such as a bridge or bridges, and public spaces, parks, benches, and pavilions. Moving into recent applications proposed by researchers. One notable proposed application by researchers is NASA and other space organizations utilizing Shotcrete 3D printing for future use in space and on Mars and Moon. Here is a list of more defined applications reported by past researchers. And one, in fact, is the load bearing and slender wall structures. ceiling and roof elements, shell and spital structures, bridge components, facades, and urban furnitures. The 3D printing, Shotcrete 3D printing equipment, typical equipment that researchers use and develop. So if you look at the slide here, you can see this is actually a robotic hand. And with this, you see the printing robot, which is actually the robot itself, and the printing nozzle, the nozzle feed rate, the nozzle distance, and actual product spray wall that it's doing. And encapsulating all of this, what you have to reckon or what is purported by the researchers is that you first have to have a plan. You have the plan and then you put the plan in place so that the robotic hand can make the production or the final product. And you can see here in the slide what I'm talking about. And finally, here are two typical end product of Shotcrete 3D printing. On the left, one can see the prototype spatial structure, which is actually a component of a roof system or formwork done by researchers in Germany back in 2019. On the right side, you can see vertical reinforced wall component, which they actually use ultra high performance concrete sprayed over 80 moles, which was done by researchers in Melbourne, Australia back in 2020. So, therefore, one can see that researchers are looking into the future with great ideas for shotcrete 3D printing. Thank you.
On this slide, we're comparing the technology we're focusing on, Shotcrete 3D printing, with extrusion-based 3D printing. Even though both fall under the umbrella of construction 3D printing, they behave pretty differently, and each one has its own strengths and weaknesses. Starting with extrusion-based 3D printing, this is the method most people think of when they picture 3D printed buildings. The printer pushes material out of a nozzle in long, smooth beads, stacking them layer by layer. Because of that controlled nozzle movement, extrusion tends to be very precise. You get consistent layer height and cleaner edges, but you're also mostly limited to straight walls and simpler shapes because the material needs support from the layer underneath. That's why printed buildings often have the very recognizable stacked bead look. The whole process is pretty clean and predictable, which makes it easier to manage on site. Now on the right side is shotcrete 3D printing, which works almost the opposite way. Instead of extruding a bead, shotcrete is sprayed at high velocity, just like traditional shotcreting. This gives you two big advantages. It's much faster and it's way more flexible when it comes to shape. You're not restricted to perfectly vertical lines. You can build curves, angles, and more free-form designs that extrusion struggles with. That's one of the main reasons researchers are so interested in this approach. But there are some trade-offs. Because the material is sprayed, it's harder to control overspray and layer thickness, and it usually creates a rougher surface that needs to be smoothed out afterwards. It's not as clean or precise as extrusion, but it opens the door to designs that extrusion simply can't make. So overall, extrusion is great for price, precision, and neatness, while shotcrete really shines when you want speed and more creative geometry. Neither method is automatically better. The right choice really depends on what you're trying to build. On this slide, we're comparing extrusion-based 3D printing shown in image A with shotcrete 3D printing in image B. In the extrusion example, you can see how the nozzle lays down smooth, consistent layers, This method gives very precise control and ends up with that bead look I talked about in the last slide. In contrast, the Shotcrete image shows the material being sprayed at a high velocity. This allows for much faster construction and lets you create more complex or free-form shapes. The trade-off is that the finish is rougher and harder to control compared to extrusion. So overall, extrusion gives precision and clean layers, while Shotcrete gives speed with a little less control. Recent studies on construction 3D printing show that most of the current work focuses on extrusion-based systems, where concrete-like materials are placed in controlled layers. Researchers highlight the advantages of automation and consistency, but they also point out clear limitations, mainly the restricted shapes these systems can create and the difficulties involved in adding traditional reinforcement. In contrast, traditional shotcrete has been used for decades and is known for its excellent adhesion, dense compaction, and ability to be applied on vertical, curved, or overhead surfaces. These qualities make it appealing for adaptation into automated or robotic printing systems. More recent work exploring shotcrete 3D printing suggests that it could solve some of the limitations seen in extrusion, because the material is sprayed rather than extruded. Robotic shotcreting can create curved or free-form shapes and may even improve interlayer compaction and bonding. Researchers also emphasize how important the mix behavior is, especially the use of accelerators, fibers, and rheology control, to ensure the material can be pumped, sprayed, and still support new layers. At the same time, the literature makes it clear that the technology is still developing. There is limited full-scale structural testing and no established standards for mixed design or performance yet, showing that while shotcrete 3D printing is promising, it still needs more research before widespread adoption.
Shotcrete 3D printing blends the speed of traditional shotcreting with the control of robotics. It's great for complex shapes and larger elements, though it still needs better mix standards and improved layer bonding. Even with those challenges, the research and real-world tests show a lot of promise. As development continues, this could become one of the more practical and 3D concrete printing.